This PowerPoint finishes up Chapter 7, and it presents an alternate way for finding empirical formula other than the percent composition that we went over in the last PowerPoint. And this one is combustion analysis. One of the things I like about combustion analysis is it emphasizes how to talk about how many moles of a particular element you have within a compound. And that's a little bit different than the conversion factors we've done up to now. So the conversion factors we've done up to now are going from grams of a particular compound to moles of that same compound, right, using molar mass, converting back and forth between molecules of a certain compound to moles of a certain compound, using Avogadro's number as a conversion factor, and then in stoichiometry, how to go from moles of a particular compound to moles of a completely different compound using mole ratio. What combustion analysis does, and I think some of you have probably seen these type of question in a worksheet too, is if you have a compound like CH4, let's say you have 1 mole of it, and I ask you how many moles of hydrogen are in 1 mole of CH4, you would say 4. So you just multiply the subscript times how many moles of the substance you have. And that's what we'll be doing in combustion analysis. So combustion, just to remind you, this is a reaction that everybody should be very familiar with now, and you should be able to write out a balanced combustion reaction for any fuel I give you, because the other reactant is always oxygen. Note that oxygen is a diatomic, it's O2. The products are always the same for combustion of a hydrocarbon. You get carbon dioxide and water. What combustion does is it literally burns a sample of an unknown and then analyze the precise amount of carbon dioxide and water that's produced from the combustion. And then through stoichiometry, we can backtrack and figure out what the ratio of carbon to hydrogen was, and therefore find the empirical formula. And so, for example, let's say that you get 2 moles of carbon dioxide. Say you recover 2 moles of carbon dioxide. That tells you then that that's how much carbon you started with. So there's only one source of carbon on both sides of a combustion reaction. Okay, so they have a 1-to-1 relationship. Now, water's it's not 1-to-1, but it's still pretty straightforward. You can see that water is the only source of hydrogen on the product side. Notice that the stoichiometry, though, is that it takes 2 of hydrogens on the reactant side to make 1 water. Okay, in other words, there's a 1-to-2 relationship. So carbon has a 1-to-1 relationship. However many moles of CO2 are measured in the product side, that is the same number of moles of carbon that were in the original fuel. You need to be careful with hydrogen because it's not a 1-to-1 relationship. So for every 1 mole of water that is collected or measured on the product side, that means you started with twice as many hydrogen in the original fuel. Remember, because it takes 2 of these hydrogens in the original fuel to make 1 water. So just be careful of that mole ratio there. All right, so let's walk through an example. I'm gonna give you a sample and then the steps. I'm gonna work it out and give you the steps as I go. So the first thing, this is a typical combustion analysis problem. Well, you will be given the quantity, the grams of carbon dioxide and water that are formed from combusting some unknown hydrocarbon. So the first thing you need, of course, first thing we always do, right, is to convert moles, right? You can't compare different substances unless they're both in moles. So we know how to do that, right? Take the given amount, grams of CO2, divide by the molar mass of CO2, And we want to take that back to carbon. Remember, we are looking for an empirical formula with this generic format, right? A hydrocarbon. All right, so there, as I said in the last slide, there's a 1-to-1 mole ratio of carbon to CO2. All right, for every 1 carbon in the original fuel, it makes 1 CO2. So that's pretty easy. So we could say, okay, we have 0.0300 moles of carbon. So I'll just put that there. Now let's do the same for hydrogen. Convert the hydrogen to, convert the water that was produced to hydrogen atom. So water molar mass is 18.02. Okay, that gives us the moles of water. Then be careful here for the mole ratio. Remember, for every 1 mole of water that is collected and measured, there were 2 hydrogen atoms, 2 moles of hydrogen atoms in the original fuel. So we then get that the relative moles of hydrogen are 0.0600. All right, so obviously you want these to be whole numbers to get an empirical formula, so you're going to take the ratio of these, okay? This is an easy one. There's clearly twice as much hydrogen as there is carbon, okay? So the empirical formula is CH2. Here's one for you to try. I am going to give you a couple of hints, but I'm not going to work it completely out for you. My hint is, look at this one. It's got carbon, hydrogen, and oxygen, okay? So from the combustion reaction, I'll just write it generically up here. So this is what we've got, okay? Because they said there's oxygen. But it still makes the same products, okay? It still makes carbon dioxide and water. But oxygen is present in every single substance, so we cannot do a nice, neat, straightforward stoichiometry calculation to figure out how much oxygen was in the original product. So you're going to work this problem like we did the last one. You're going to start out working it the same, where you're going to convert grams of CO2 to moles of CO2, right? And then use a mole ratio to get moles of carbon that were in the original product. You're going to do the same thing for water, right? Moles of water, then you're going to use the correct mole ratio to get to moles of hydrogen. How are you going to figure out oxygen? It's quite a bit more work when you have oxygen included in your original fuel. So what you need to start with is be aware of how much the mass of the total fuel was 100 grams, right? So if we can figure out the mass contributed from carbon, right, and the mass contributed from hydrogen, then what's going to be left over is the mass contributed by oxygen. So how can you get the grams of carbon in this original compound and the grams of hydrogen in the original compound? You're going to get them from here, right? You know how to get grams from moles. All right, so that is my hint. Let's see how you do.